This is Mr. Beck Does Your Homework. This is AP Physics, Homework 9.1, question number 14 and 15. The question says, three positive point charges are arranged in a triangular pattern in a plane as shown. Find the magnitude of the net electric force on the 7 nanocoulomb charge. Now what I see is that the 8 nanocoulomb and the 7 nanocoulomb are positive, so they're going to repel, and that will push with a force down and to the right. I'll call that force 1. I also know that acting on the 7 nanocoulomb charge is the 5 nanocoulomb charge, again a positive. Those positives will repel and push the 7 nanocoulomb charge up and to the right. So these are my two forces that I'm going to have to add. Now I know I'm going to use Coulomb's law to figure out the magnitude of each one of these forces, and that's K times Q1 times Q2 divided by the distance between the charges squared. So in the case of F1, I have K, which is 9 times 10 to the 9th, or in this case 8.98755, but you can use 9 times 10 to the 9th, that's well within 1%, times the magnitude of the first charge, 8 times 10 to the minus 9th, nanocoulombs is times 10 to the minus 9th. Q2 is 7 times 10 to the minus 9th, and then I have to divide it by the distance between those charges squared. Well, I know that those charges are a distance of the hypotenuse of that right triangle that's 4 meters on a side. So that would be 4 squared plus 4 squared, square root is the distance, and then I want to square that because the denominator in this Coulomb's law is squared. So you see that you really don't need the square root or the squared there. It's just going to be 4 squared plus 4 squared in my case. So I can multiply that and divide it and get an answer for the magnitude of F1. I can do the same for the magnitude of F2. Well, now I've got these two forces, and I'm going to have to add them together, and you can see that the vectors are going to add to something that's a little bit down and to the right, because for me the 8 nanocoulomb is pushing a little more than the 5 nanocoulomb. So in this case, typically what I would do is take each vector force, split it into its components by using sine theta and cosine theta. In this case I have a 45 degree, so it would be sine 45 and cosine 45 times the magnitude of F2. I do the same with F1, and then I could take my horizontal components and add them together. I could take my vertical components and add them together, vector add, one up, one down, and the resulting vector is going to be the sum of those two using the Pythagorean theorem, and that would give me my final result. Now that's going to involve a lot of components and dividing and subtracting and adding and all of that, but there's actually an easier way to do that, and this comes from the monkey problem, if you remember that from before. And when we have two forces and those forces are at a 90-degree angle, which these are because each one is 45 degrees up and down, well that means that I can also identify this as a 90-degree angle between force 1 and force 2 to get my resultant. So if I slide force 2 down, I've got that rectangle. So now I've got a right triangle where the resultant vector is merely a squared plus b squared equals c squared, using f1 and f2 as a squared and as a and b. So this is an easy shortcut around all of that vector addition and splitting into components that we did before. So once I've got that, that is going to be my answer to question 14. So simply f1 squared plus f2 squared square root. Question 15 is looking for this angle right there, but you know that the bigger angle is a 45 degrees. If I want that small angle between the red vector and the axis, in my case it's going to be a negative angle, all I have to do is find the measure of this theta in yellow, because if I know that, then I can easily find the other one by subtracting it from 45. Well, to get that yellow angle, I know that the tangent of that angle is going to be f2 over f1 in my case. So make sure you've got your triangle drawn, and you can see that f2 over f1, I can do f2 over f1 and find the inverse tangent of that to get theta, and then 45 minus theta will give me my angle. In my case, since I've got a bigger charge up top with the 8 nanocoulomb than at the bottom, that is going to be a negative resulting angle compared to the x-axis. So it looks to me just visually like, negative 15, 20, 30 degrees, something, 15 or 20 degrees, something like that.